All right, here we are. Stats, box plots, and standard deviation. All right, so this is one of the last kind of major topics of this unit. And again, it's still just all about describing data, presenting it in such a way that people can draw meaningful information out of, a sea of numbers, and then hopefully use that information to make better, more informed decisions. So we're going to start by talking about the five number summary and its graphical representation, which is the box plot. So this was on that very first warm up we did in this class, just to see if you remembered what some of these things were. But the five number summary is a list of numbers showing the lowest value, Q1, the median, Q3, and the largest value in that order. All right, so if you're presenting a five number summary, you shouldn't just randomly put the numbers down in any order you want. They should be listed from smallest to largest, not from largest to smallest, and certainly not just randomly dispersed. So a lot of times you'll just see them, and it'll just be min, Q1, median, Q3, and the max. All right. But those five numbers give us a pretty good idea of sort of how the distribution is spread apart. It tells you where the center is, gives you an idea of how spread out the data is. It gives you an idea whether there could be outliers or how far it stretches out. So there's a lot of information that can come from just those five numbers. Now, the box plot is sort of the graphical representation of the five number summary. So it's a display that shows the five number summary across a number line. All right. And what it does is it just helps the viewer or the consumer of your statistics to sort of visualize what's happening. Now, sometimes this is also called like a box and whiskers plot. So these are your whiskers, this is your box. This represents your min or your lowest value. This represents your max or your highest value. The line in the center of your box is the median, and then the start of your box is Q1, and the end of your box is Q3, which also means that the size of your box represents the IQR, and from one end to the other would represent the range. All right, so it can give you this sort of understanding of how spread out things are, which way your distribution is skewed, and a whole bunch of other things. So we'll look at kind of pulling that information out on the next page. One thing that's going to be new to box plots for this course is how we handle outliers. So if you made these back in algebra, it was always the min was here, the max was here. It's going to be different in this class. The whiskers only extend to the smallest / largest non-outlier. All right, so if you have an outlier, the outliers are going to be designated with asterisks. All right, this is what we're going to designate an outlier with. So we're going to just put an asterisk on the number line that designates that it's an outlier. And then the whisker is only going to go to the largest non-outlier. All right, so what we have here down at the bottom is some data from last class. All right, so this was the data set that we used at the end of last class to figure out whether or not there were any outliers. All right, and we saw that the cutoff for outliers ended up being 83.75, which meant that we did have this one outlier, and there were no outliers sort of on the lower side. Our Q1 was 15, right? And again, this is just coming from last class. But if you needed to find this information, the easiest way would just be to put it into your L1 on your calculator and run one variable stats. The median was 20, and Q3 was 40. All right. Again, all of that's just coming from last class. Now, as far as one sec. All right, never mind. These numbers were off. I thought there was something wrong there. All right, so the 15 was correct. This, I meant to say 22.5. I don't know why I had those other numbers. And this, I meant to say 42.5. Sorry about that. All right, so again, putting this in the calculator, you could get 15, 22.5, 42.5. Using our formula, Q3 plus 1.5 times the IQR. Remember, the IQR is just Q3 minus Q1, would get us this benchmark of 83.75. So if we were going to make a box and whisker or a box plot for this data set, all right, we'd start with the min, which is 5. Now, that is not an outlier, so our whisker can start right at the 5. That's fine. We're going to go until we get to Q1, which is 15. That's where we're going to start making our box. When we get to 22.5, we're going to finish off this first box and then start our second box, which is going to go all the way to 42.5, which is about right there. And now this is the part that's going to be different. So our right-hand whisker is only going to go out to the 65. All right, so there's our right-hand whisker. And then the 85 is going to be designated with an asterisk like that. All right, so in this class, the expectation is always going to be that outliers are designated with an asterisk. All right, if you make a box and whisker plot and there are outliers and you do not designate them with an asterisk, you will lose points on that. All right, it's a required part of this class is that when you make a box plot, any outliers are always designated with an asterisk. Now, this can actually be done on your calculator. So if you go to Stat Edit and enter your data, so here I have all my data entered, and then you go to second y equals, all right, which is the stat plot menu. You can hit enter, make sure it's turned on. You're going to see that there are two different box plot pictures. All right, let me unselect them so that it's easier to see them right now. There are two different box plot pictures. One of them has the box plot and then like two dots off to the right. The other one has just the box plot. We are always going to use the one with the two dots because that will tell us whether or not there are outliers. All right, it will do the graph in the way that I just described. So when anytime you're using a calculator for your box and whisker plot, you want to choose the one with the dots. You can go to Zoom 9 for Zoom Stat. All right, and that will show you your box and whisker plot. And then if you want to know the individual values, you can hit trace. All right, and then it'll tell you the min is 5. It'll tell you the Q1 is 15. It'll tell you the median is 22.5. Q3 is 42.5. It'll tell you that the end of that whisker is a 65. And then it'll tell you that this outlier out there is 85. All right, so this is the correct way to make a box and whisker plot in this class. The other nice thing about this box and whisker plot is it's sometimes an easier way to check for outliers. All right, instead of having to do the calculation Q3 plus 1.5 times IQR and Q1 minus 1.5 times IQR, you can just put the data into your calculator, bring up the box and whisker plot, and see whether or not it designated any asterisks. If there's no asterisks, you know there's no outliers. If there's asterisks, then you know there are outliers. So it's also a convenient way to be able to check for that without having to do all of the work. Now, I will say on like quizzes and tests, I will usually specify, if I just say determine if there's any outliers, then I don't care how you do it. If I say like determine if there are any outliers and like show the calculations, then you actually have to do it the long way and show me that you do know how to do this part right here. All right, but just be aware of this. Next, comparing distributions using box plots in context. All right, so we've got two different box plots. What can we say about these two different box plots, and how can we compare what's going on with these distributions? Now, to do that, it's helpful to kind of know how we can determine the shape from a box plot. So remember that the box plot is really breaking your data down into groups. So this is saying that the first 25% of your data spans this range. All right. The second 25% of your data spans this range. The third 25% of your data spans this range. And the fourth 25% of your data spans this range. So what we can see in both of these graphs is that the back half of the data is spread over a much larger range than the front side of the data. So what that tells us about the shape is that both of these are right skewed, right? Because we have a bunch of observations on the low side, and then the observations on the high side are getting stretched out over a longer interval. Same thing here. We've got a bunch of condensed observations here, and then they get stretched out over a longer interval. So I just, over on the side here, I just kind of want to demonstrate this. So there we have our right skew. If we're looking at a box plot for a right skewed graph, you're going to have the data on the left-hand side be really compressed because, again, it's 25% of the data. And if you have a lot of observations, you're going to get to that 25% really quickly. And then the right-hand side, where the tail gets more narrow, is going to get stretched out and require a larger interval to capture, like 25% of the data. So a right skewed distribution might have a box plot that looks like this. A left skewed distribution will have basically the opposite. So you'll have the long tail here. This box will be longer, and then you'll be more condensed down on this side. And then last but not least, if you have a symmetric distribution, you would expect that your box plot to be relatively balanced, all right? And most of the four intervals being approximately the same size, all right? So again, just kind of looking at this here, remember the asterisks are outliers. This would be the largest non-outlier. And again, the height of the box is your IQR. So just stuff that you can read from these. Now, as far as comparing the two distributions, both distributions are right skewed. And the reason we know that is that the distance from the min to the median is greater than the distance from the median to the max, which again is just another way of saying the top part of the graph or the right-hand side of the graph is more stretched out than the left-hand side or the bottom there. Now, as far as the center of the distribution, if we're comparing these, we can see that since both are right skewed, we should really measure our center with the median. So we can see that they're pretty similar. All right, so we could say the travel time is fairly similar. Though New York does have a higher Q1 median and Q3. All right, so they're all higher. Most of them are just slightly higher. The median and Q1s are slightly higher. Q3 is substantially higher, but they're all higher. So New York does sort of trend a little higher when we're comparing these distributions. The spread, how spread out things are, we can say that travel times are more variable in New York as demonstrated by the height of the boxes, which again represents the range. I mean, sorry, not the range, the IQR, and the overall range. All right, so when we're comparing spread, we can see that the middle 50% of the data is more spread out for New York, and the entire range of the data is more spread out. Down here in North Carolina, it has a smaller IQR, and it has a smaller range. So we would say that it's more variable, travel time is more variable in New York than it is in North Carolina. And we see that both by the IQRs and by the ranges. And then outliers, you just would always want to comment on if there are outliers. So we would say New York has one outlier at 85 minutes. North Carolina has none. All right, but again, if we're sort of comparing these two distributions and reading these graphs, this is the type of comparison that we could write across all four of our metrics. Because remember, anytime we're describing a distribution, we want to hit on the shape, the center, the spread, and the outliers. So we can get that information from these graphs. We can figure out what the shape is by looking at how the graph is balanced. We can figure out what the center is by looking at Q1, the median, and Q3 and kind of seeing where they fall. All right, we can look at the spread by looking at the height of the box, that's our IQR, or the total range from one end of the graph to the other. And then we can talk about outliers because the asterisks will identify any outliers. So all the things that we're supposed to talk about regarding distributions, we can gather and read from one of these charts as long as you know how to interpret them. All right, and that's one thing that you're going to need to be able to do is interpret these graphs. If I were to just give you one of these graphs, you should be able to tell me about the shape, the center, the spread, outliers, and so on and so forth. But you have to know how to interpret one of these graphs and everything that it shows. All right. So next up, and this is actually the last sort of statistic that we're going to talk about in this unit, but we're going to talk about it a lot because it's a major part of our course going forward. All right, and that is the standard deviation. All right, so a lot of times you are going to see the symbol written as this, all right, S sub x. And this is the average distance each observation falls from the mean. All right, so it's the average distance that each observation falls from the mean. So we're going to get into the actual calculation in a second, but I just want to make sure that we've got sort of just our heads wrapped around what we're doing. So let's say you have a bunch of points, all right, and these points are on a number line. All right, so you've got a number line here, all right, and let's pretend that the mean of these points falls right here. All right, this is the mean. All right, maybe I'll put another one over here. All right. So what standard deviation is doing is it's looking at how far each point is from the mean. And it might say, oh, this one's 1 away from the mean. And oh, this one's 4 away from the mean. And oh, this one's 5 away from the mean. And this one's 7 away from the mean. And this one's 9 away from the mean. All right, so it's finding out how far each point is from the mean, and then in both directions. It might say, oh, this one's 1 away from the mean in the other direction. You know, this one is, let's just say, 3 away from the mean in the other direction. This one is 6 away from the mean in the other direction. This one is, we'll say, 10 away from the mean in the other direction. But it's telling us how far away each of those points are from the mean. And then we would basically average those values together. All right, so that's the idea of what we're doing. Now we're going to see that the calculation isn't exactly what I'm describing, but this is the way you want to think about it. You want to think about it and say, all right, I have all these data points. Somewhere there's a mean, and I'm figuring out how far each point is from that center mean, and then I'm averaging all of those values together so that I can say on average, you know, my data is 3.7 from the mean, or my data is 5.6 from the mean. But it's saying that, okay, we're figuring out how close things are to the center point. So for example, you know, if you had a distribution where this was your mean and all of your data was really close to the mean, all right, you would expect that that would have a low standard deviation because everything is really close to the center or the mean. If you had a situation where the data was really far from the mean, right, really spread out, this would be a high standard deviation situation because you're measuring the average distance from the mean. These are all really far from the mean, so the average distance is going to be a larger number. These are all really close to the mean, so that average distance is going to be a small number. And again, this isn't the exact calculation, but it's the visual premise of what we're doing here. All right, so let's look at the exact calculation and kind of walk through how that's going to work. All right, so a couple of things here. It is calculated by finding the average of the square distances and then taking the square root. The average square distances is called the variance. So we're not going to use the variance right now, but the variance is the value before you take the square root. All right, so we're going to be taking the square root as part of our calculation. And the number that you have before you take that square root is called the variance. Now, the formula is as follows. It's the square root of the summation, which just means add together, of x sub I minus x bar squared, right? So what does that mean? X sub I is just your observation, so that's your data point. X bar is your average. So we're subtracting these to figure out how far they are from the mean, but that's going to give us positive and negative numbers. So we're squaring that to get rid of the positive and negative numbers. And then we're not actually going to divide by n, we're going to divide by n minus 1. All right, and that's a little, why we divide by n minus 1 is a little advanced for right now, but it deals with this concept of a biased versus an unbiased estimator, and we'll talk about that later in the year. But basically, what we're saying is that because it's a sample, it's not everybody, we're probably underestimating how spread out things are. So by dividing by n minus 1 instead of n, it's going to make our value a little larger to basically say, hey, we're probably missing something, so let's bump our number up a little bit. Now, when we have the entire population, all right, so when we're not taking a sample, but we're talking to everybody, we don't have to make that adjustment because we've captured everybody. So it's the same exact formula, only instead of dividing by n minus 1, we divide by n. So this is more of a true average because we're dividing by n. This is sort of us adjusting the standard deviation up because we recognize that when we take a sample, we're probably missing something. So this adjusts our value up because the sample is missing some of the data. All right, think about this way. If you were surveying, like, you know, people's height at Ichabod Crane, unless your sample ended up with the smallest person at Ichabod Crane and the tallest person at Ichabod Crane, you'd be underestimating the range, all right? Because you'd be saying, oh, I think it goes from this to this, but unless your sample was lucky enough to get the tallest and the shortest person, you'd be underestimating it. It's the same idea with standard deviation. We just assume that we're missing how spread out things are, so we make this adjustment to sort of boost the value. All right, so let's take a look at how this actually works via like a hand calculation. So here we have a bunch of observations. This is how many pets somebody has. So person 1 has 1 pet, person 2 has 3 pets, 4, 4, 4, 5, 7, 8, and 9. Right? The first thing that we need to do to be able to calculate the standard deviation is know what the average is. All right, so we would have to add these together and say 9, 17, 24, 29, 33, 37, 41, 44, 45. So these all sum to 45. So X bar would be 45 over the 9 people, or 5. So we're going to start by figuring out how far each observation is from that average. So we've got 1 minus 5. This one is 4 below the average. 3 minus 5 is 2 below the average. 4 minus 5, 1 below the average. 1 below the average. 1 below the average. This one is right at the average, so the distance would be 0. 7 minus 5 is positive 2. 8 minus 5 is positive 3. And 9 minus 5 is positive 4. All right? So these numbers right here are our deviations. They are how far each observation falls from the mean. All right? Now, if we were to average these numbers together, watch what happens. Negative 4 plus negative 2 is negative 6. -7, -8, -9. Now we're dealing with positives. So -9 plus 0 is still 0. -9 plus 2 is -7. Plus 3 is -4. Plus 4 is 0. And the positives and the negatives cancel each other out. All right. That's a problem. All right. Because if they cancel each other out, I would say, oh, the average distance is 0. And pretty clearly, the average distance is not 0. So we get around that by squaring them. So we take all of these values and we square them. Because if you do -4 times -4, it's going to become positive. So we've got +16, +4, +1, +1, +1, 0, +4, +9, +16. Now what we're going to do is we're going to add all of those together. All right, so if we add all of these together, let's see what they sum to. All right, so 16, 4 is 20, 21, 22, 23, 27, 36, 46, 52. So these sum to 52. All right, so what we've just done is this part of the formula. We've summed xi minus x bar squared. All right, so if we're thinking about our formula here, and we've got the summation of x sub I minus x bar squared, and then we're using a sample, so we're going to use n minus 1 instead of n. All right, this 52 is the result of this part right here. So now we've got the square root of 52 over n minus 1, which is 9 minus 1. All right, so this part is our average, only we didn't calculate the average. We calculated the average when those distances were squared. So our last step is to take that square root to get it back down to just like a regular average. So anyways, this would be the square root of 52 over 8, all right, which is the square root of 6.5. Now, this 6.5, before we take the square root, that's that number that I was saying earlier is our variance. All right, and then after we take the square root, and we take the square root of 6.5, we get a value of 2.5495. I'm just going to round that to the nearest hundredth. So 2.55. All right, this would be our final standard deviation, which is basically the average distance from the mean. Now, the units for this would be 2.55 pets. All right, so we were observing pets. Standard deviation always has the same units as the mean. All right, so the mean was the average number of pets. So the standard deviation is 2.55 pets, which is basically saying most of our observations are 2.5 pets from the mean of 6, what was the mean? 5 pets. So if the mean is 5 pets, most of our observations are within 2.55 pets, or put another way, on average, our observations are 2.55 pets from the mean. Some are closer, all right? Some are further away, but those distances average out to be 2.55 pets, all right? And that's what the standard deviation is measuring. It's measuring the average distance from the mean, all right? And it does it by finding the differences, squaring them, taking the average with this little adjustment here, and then taking the square root at the end to undo the squaring that we did here. So we squared it to get rid of the negatives so that they wouldn't cancel out. and then we square root it to sort of undo that at the end and get us back to the same units and the same measurement. All right, so that wraps this up. I hope this was helpful, and as always, let me know if you have any questions. Bye.